Since cargo ships are designed based on cargo-laden conditions, various problems may occur when the ship is in ballast condition. Ballast operations are conducted to avoid these problems. This DVD introduces methods to carry out ballast operations safely and securely. First, let's look at what ballast operations are and their purpose. Since a ship's draft is shallow while in ballast condition, it's susceptible to wind and wave impact. As a result, rolling increases and hull stability deteriorates. To improve hull stability, a ship's ballast tanks are filled with seawater. When loading a ship with cargo, seawater in ballast tanks is discharged. Such seawater filling and discharging are called ballast operations, which are conducted either by gravity or ballast pumps. Please note that improper handling of pumps and/or valves may result in various accidents. Shown here is a pipeline laid on the ship's bottom, through which seawater flows for ballast filling or discharging. Joints that connect the pipes are called dressers. There are cases where dressers are damaged. This is an example of a water leakage accident due to dresser breakage caused by abrupt valve operation. Valves are provided where the pipeline is connected to ballast tanks. The pipeline is fitted with many such valves. Improper valve opening or closing can cause accidents. This is an example of an accident caused by valve rupture. In this accident, corrosion in the valve body, combined with sudden pressure change due to pump stopping, ruptured the valve body during a stroke to produce a hole in it. To prevent such accidents, you must have a good understanding of the procedures for proper handling of pumps and valves. Water pressure is a vital factor affecting ballast operations. Water pressure is expressed by the term water head pressure. Let's consider a 10-meter tall water column. As 1 cubic centimeter of pure water weighs 1 gram, a 10-meter tall water column with a basal plane of 1 square centimeter is equivalent to 1,000 grams, or 1 kilogram. Therefore, the water pressure placed on the basal plane is 1 kilogram per square centimeter. This pressure is referred to as 10-meter water pressure head. In other words, water pressure head means pressure translated from the height of a water column. When the water level inside the ballast tank is higher than that of the level of the seawater outside, ballast water can be discharged by gravity, thanks to the water pressure head inside the tank. Discharging by gravity stops when water pressure head becomes zero, as the tank's water level comes down to the same level as the seawater outside. To continue to discharge further from this state of balance, it's necessary to use a pump, pushing the water out with a pressure higher than that of the sea surface. Cargo is loaded under this condition. As cargo is unloaded and the water level inside the ballast tank becomes lower than the sea surface, ballast water is gravity filled into the tank thanks to water pressure head of the seawater. Ballast filling stops when the water pressure head becomes zero, as the ballast water level rises to become equal to that of the sea surface. To continue to fill ballast water further from this state of balance, it's necessary to pump water in with a water pressure head higher than that inside the tank. There are various pump types. Of these, centrifugal pumps are commonly used in ship ballast operations. With centrifugal pumps, a motor is used to rotate a vane wheel called an impeller. The centrifugal force thus generated is used to send water out. Let's have a look at this principle. Put some water in a cylindrical container and turn it around the container's axis as the center of rotation. A centrifugal force works on the water and pushes it toward the container wall, making the water surface form a parabolic arch. As the rotation speed is increased, the centrifugal force becomes stronger to such an extent that the water goes over the container's brim and spills out. If the overflow is collected at this time, and at the same time, a space is created in the bottom of the container through which to send in water continually, the water rises from the bottom to the top of the container. This explains the principle of the centrifugal pump. With actual pumps, when the impeller is rotated at a high speed in a casing filled with water, pressure at the impeller's center area drops. Then, pushed by the atmospheric pressure, the water is allowed to flow into the pump through a suction pipe. The water, which has been splashed by the impeller's centrifugal force, gathers in the volute casing and gains in pressure before flowing out of the delivery pipe. The height to which a pump sucks up water is called pump head. The height from the pump's base plane to the water suction level is called suction head, while the height from the pump's base plane to the water discharge level is called discharge head. And the total of both heads is called total pump head. Total pump head means the height to which the pump actually transfers water from a low water level to a high level. A pump's performance capability can be expressed in terms of relation between total pump head, H, and discharge amount, Q. As shown in this graph, the points where the total pump head and the discharge amount cross form a curve peculiar to each pump. When the total pump head is high, the discharge amount becomes small because a greater pressure head is required. As the total pump head comes down, the required pressure head decreases and the discharge amount increases. Pump output refers to an amount of work with which a pump pushes up a certain discharge amount of water to a certain pump head. The relation between the pump output P and discharge amount Q also shows the pump's performance capability. Cavitation is one of several phenomena you should avoid when operating cargo pumps. When water flows fast through a region, the pressure falls below the water's vapor pressure, causing vapor bubbles to form. As they collect, these vapor bubbles create a cavity, a phenomenon known as cavitation. When these bubbles break, they produce minute vibrations that cause abrasion. Repetition of such vibrations leads to damage to parts of the pump. Water boils at 100 degrees Celsius under 1 atmosphere, or 0.1 megapascals. But on top of Mount Fuji, the atmospheric pressure drops to 0.06 megapascals, causing water to boil at 87 degrees Celsius. As a result, the critical pressure at which a liquid begins to boil under a certain temperature is called saturation vapor pressure for that temperature. The lower the saturation vapor pressure, the lower the boiling point. In other words, vapor bubbles and cavitation occur where water pressure is low. Here's an example of cavitation. It occurs in the periphery of the bell mouth during discharge from the ballast tank. In the event the suction speed increases as the water level drops, cavitation is prone to occur in the periphery of the bell mouth. When it comes to pumps, cavitation is liable to occur in areas around the impeller. Bubbles generated can cause abrasion, and vibration can damage the impeller. Typical damage to pumps due to cavitation includes decreased pump efficiency, decreased discharge flow, and noises and vibrations, which eventually make it impossible to continue operating the pump. Impact pressure promotes corrosion and abrasion of the impeller, leading to shorter pump life. To prevent cavitation, raise the pump's suction pressure. In terms of pump operation, decrease the pump's discharge flow by reducing the discharge valve opening. To raise the suction pressure, decrease the suction line resistance. With some ships, suction line resistance is decreased by keeping valves on the suction line side fully open at all times. Their opening is not reduced. If a pump draws in air while in operation, a noise is produced, and the amount of seawater discharged decreases, significantly lowering the pump's operating efficiency. Also, the amount of seawater being discharged will drop to zero in an instant once the pump has drawn in a large amount of air. Why? When a small amount of air is drawn into the pump, the air passes out of the pump together with the seawater. But if a large amount of air has entered the pump, it gathers and gradually spreads to the pump periphery, decreasing the centrifugal force the seawater receives from the impeller and disabling the pump from discharging. If the discharge amount is extremely small, there are cases where unnoticeably small amounts of air gather within the pump and build up to a level that could disable the pump. If left as it is, seawater in the pump will run out, resulting in burn. Here you can see how air drawing occurs during discharge operation. In the beginning, the pump's pressure gauge reading is stable. Suction in the bell mouth area appears to be working smoothly. But now a vortex appears and sucks air in from the water surface, the beginning of the air drawing process. As the water surface level lowers further, the water rapidly whirls around the bell mouth while rolling. This makes it easy for the pump to draw in a large amount of air. At this time, the pump's pressure gauge reading becomes unstable. As a corrective measure, reduce the pump's discharge valve. Then the gauge resumes stability. There are several ways to prevent air drawing. Purge air thoroughly before starting the pump. To deal with air drawing due to a suction vortex at the bell mouth, decrease the suction flow from the bell mouth by reducing the discharge valve opening to decrease the discharge amount. Note beforehand the water level at which the pump begins to draw air, and stand on the alert as the water approaches the critical level. You may use other tanks with a suitable water level to continue discharging. With some ships, cargo planning is based on the hull with trim by the stern. It's the suitable condition to discharge all the remaining ballast. If flow velocity within the pipeline suddenly changes due to valve operation at the start of or during pump operation, the pipeline internal pressure increases momentarily but sharply. This phenomenon is called water hammering. Water hammer can damage the pump casing, valves and pipeline. Shown here is an experiment reproducing the process of how water hammer occurs. The apparatus used is an acrylic pipe fitted with a butterfly valve, through which pressurized water is passed. We observe the behavior of the U-tube attached to the pipe outlet. The acrylic pipe corresponds to the ship's pipeline. The U-tube corresponds to curved sections and pipeline dresser. The section of the acrylic pipe from the valve beyond is of negative internal pressure. In actual ballast operations, there are cases where cleaning with an eductor is carried out in the final stage, which calls for the ballast line pressure to be negative. This equipment simulates such a condition prone to accidents. First, let's look at a case in which the butterfly valve is fully opened suddenly. The U-tube is movable. When pushed by the water force, it moves back and absorbs the impact. With an actual pipeline, such impact cannot be absorbed fully, resulting in damages such as cracks. Damage to the dresser joint is typical. Now we'll review this process using an image simultaneously shot from 3 directions. Next, let's see the case in which the valve is opened slightly and stopped as is. No impact is placed on the U-tube. With the actual pipeline too, it can be understood that there will be no damage to the pipeline if you open the valve slightly and stop it as is. In ballast operations, attention should be paid to valve opening and closing. If a valve is abruptly opened or closed, it causes a sudden change in pressure within the pipeline. As a result, the valve can be damaged. Also, the dresser joint may break due to excessive load on it. The key to avoiding such troubles is to open or close valves slowly. It's also important to reduce the amount of flow in advance so that sudden pressure impact will not be placed on the pipeline. In addition, general points to remember for avoiding water hammer are as follows. Pay attention to the difference in pressures in both ends of the valve. Begin ballast operation with a small capacity and at a slow speed. And fill the ballast line with seawater and confirm that the line has positive pressure. Pressure surge is a factor of possible danger with valve opening and closing. It takes place when the flow velocity suddenly changes inside the pipeline filled with fast-flowing water due to abrupt opening or closing, whether remote or manual, of butterfly valves. In the event of a pressure surge, a high-pressure face propagates through the pipeline at a velocity faster than the speed of sound, causing damage to structural parts of the pipeline. So valves must be opened or closed slowly. With butterfly valves, since flow is not proportional to valve opening, remember that a large quantity of water may flow even if the valve opening is small. In short, open valves gradually by inching Stop when slightly open and observe the state of things for a while. For valve closing, also do it gradually by inching. We can go so far as to say that most of the troubles associated with ballast operations can be avoided unless you open and close valves abruptly. Now we'll conduct a ballast operations simulation, interweaving scenes of actual operations. While introducing the ballast line makeup responding to specific operations, we'll also provide you with a summary of points to remember for ballast operations. To carry out ballast operations, you must fully understand the ballast pump structure and its characteristics, as well as your ship's ballast system. Sticking of a tank's air vent and so forth can cause the tank to expand or shrink, which may damage the hull. Therefore, make it a rule to conduct inspection and maintenance in your daily routine. For ships with cargo holds into which ballast water is loaded, be sure to confirm that their cargo holds are ventilated. To begin with, set all valves at appropriate openings. While in operation, only operate the valves to be used. To avoid wrong valve operation, secure a cap on each of the valves not in use. When opening or closing valves, make sure to pay attention to the pertinent pressure gauges. Also check the pertinent level gauges from time to time. When carrying out any task, never fail to answer back, check, execute, and report. Now we begin filling ballast water by gravity. Put the valve line up in the proper order to bypass the ballast pump. To the extent possible, conduct ballast water filling into an empty main ballast pipe, either via an opening control valve or from the lower pressure tank. When the main pipe internal pressure is negative, inch open the pipe slightly and observe the state of things for a while, then fill ballast water slowly. After ballast filling by gravity is over, let's now proceed to filling by means of ballast pump. Before starting the ballast pump, completely close the discharge valve. Centrifugal pumps are commonly used as ballast pumps. Start the pump with its discharge valve fully closed to avoid an overload at the start of the pump and to minimize surge pressure. Before starting the ballast pump, attend to the following. Communicate closely with the engine crew to avoid any accident due to lack of communication. Confirm that the power supply is switched off. Purge air. Confirm that there is no abnormality with the pump's rotary shaft. Confirm that the suction valve is open and the delivery valve is fully closed. Just before starting the pump, check the procedures again, following the order of operation, abiding by the pipeline layout diagram. Start the ballast pump. After the pump has been started, check the ballast pump electric current value, discharge pressure, and suction pressure. When changing ballast tanks for filling, open the tank suction valve to be filled next, then close the suction valve attached to the ballast tank that has completed filling. Filling of all tanks has been completed. Stop the pumps by closing the ballast pump discharge valves and then close the tank's valves. Next, let's see the steps for ballast water discharge by gravity. Operate valves to put the line up in the proper order, bypassing the ballast pump. Ballast water discharge by gravity begins as the tank's valves are opened. Next, we'll proceed to ballast water discharge by ballast pump. The ballast pump starting procedures are the same as for filling. Make sure to conduct air purging from the pump and confirm the state of valves and gauges. Watch water level, since cavitation occurs as the level drops, which causes the waterhead pressure from the pump suction valves to decline. As the water level drops further to approach the tank bottom, now exercise precautions against air drawing. Watch the gauge carefully and readily respond to the risk of air drawing. When ballast water discharge for all pumps has been completed, stop the pumps by closing the ballast pump discharge valves. Then close the tank suction valves, completing the steps for discharge by ballast pump. Officers and crew responsible for ballast operations must fully understand their ballast pump characteristics, ballast tanks and lines, valve arrangement, and other facilities. Especially, they must attend to the following while in operation. Keep watch on pressures acting on pertinent sections. Understand the pump's principle and avoid load-placing operations, such as cavitation and air drawing. And understand valve characteristics and avoid water hammer and pressure surge due to abrupt valve operation. Keeping an eye on and securely conducting operations with these points in mind is the key to ensuring safe ballast operations.